Hi, good morning, everyone. My name is Gary Etherington. I'm talking to you from JULABO UK. I'm going to be your host today, and while we wait, just to make sure everyone who wants to join us is joining us, I thought I'd introduce myself and my colleague Neil Brown. For my own part, I've had 20 plus years experience with JULABO, both working with JULABO, for JULABO, and being a customer of JULABO. So I have plenty of experience in chillers and things like that. And my job today is to try and answer some of your questions, to try and help you guys make a good decision about what chiller may or may not be appropriate for your lab and your application. I'm also going to be helped by my colleague Neil Brown, who works with me in the UK. And Neil, I'll let you introduce yourself.
Brilliant. Thank you very much. Hello, I'm Neil Brown. I'm one of the sales representatives here for JULABO in the JULABO UK. I've been working with JULABO again for probably about 18 years through distribution and and working directly. I've got vast experience in the product, so I'm going to be looking after the chat, moderating the questions and answers, and being interrupting whenever I need to, where something appropriate comes up. So feel free to get your questions into the webinar, and any kind of chat. I'll try and do live feedback as we go. So yeah, enjoy the webinar, and I'll disappear, but we'll come back in throughout the webinar.
Yep. Okay. I'm going to start in a minute or two. Just give a few stragglers the opportunity to join us. I do want this to be as interactive as possible. So if you have any questions, don't be frightened to interrupt. Also, during the webinar, we've got a couple of quick polls or questions to ask you, which is to try and get a feeling about your sort of applications and your demands, so that hopefully we can answer specific questions that you might have. Neil is going to be picking up all the questions. He's going to be feeding the ones through to me that will be of interest. We will try and answer all of them as we can. But obviously, feel free to reach out to us at any point so that we can help you understand exactly what's going on. I think I'll start in a minute or two. This presentation, it's just over 30 slides. So as a rule of thumb, that's 35 minutes. Obviously, any questions that come up, we'll try and answer them as we go along. So it might stretch a bit longer than that. And feel free to communicate to any of your JULABO channels that you may have. I think I'll give it another minute and then we'll start. I think everyone is ready just about. So I think now is a good time to get going, shall we? So let's start. The first thing I want to do today is to talk about chillers specifically, and there are different definitions from different customers and different areas of the market. So just to be really clear about what I am talking about as a chiller. Okay, so that there are two main definitions that are used. One is to replace tap water cooling, so that might be in a condenser or cooling a pump or cooling some sort of analytical device that needs to be at a static temperature. The second type of chiller that people talk about is where they want to control the temperature of something. For example, if you're putting a load of test tubes or vials into a bath and you want to hold it at room temperature or 20 degrees C, or if you want to control a chemical reactor or a metal block. Today, what I really want to focus on is replacing tap water. So you can see in this very simple diagram, this is simply replacing the tap water that you would put through a condenser. So the first question to ask yourself is why you are going to replace tap water with a chiller. Okay, there are different reasons. Okay, so we'll go through them one by one, and your demand may be completely different, maybe a combination of these or maybe a specific one of these. One of the key reasons is control and reproducibility. So like every laboratory, like everywhere in the world, you get seasonal variation on your temperature of your tap water. So in the summer, your tap water can be 15, 16 degrees. In the winter, it can be 4 or 5 degrees. You can also have different demands on site, and you can have a change in flow rates. In addition, obviously, depending where you are in the world, and if you have house mains water, some of the water quality can be really, really horrible. Neil and myself have seen areas where tap water is a horrible brown colour, and you don't want that running through your equipment. So that's one of the reasons why you may turn to a chiller. Another reason, and I've seen this at several locations, is potential flood damage. If you are running tap water through your device, so let's imagine a large glass condenser and the hose comes off of it on a Friday afternoon at 3 o'clock when everyone's thinking about going home, you have the ability that that tap can be running all weekend and flooding your lab. And I've seen that myself in a couple of universities last year in the UK, had an issue with flooding labs. And actually one of them was on the 3rd floor and the water damaged the lab it was in and the lab below that. But one of the most common reasons that's increasing right now is sustainability and costs. We have to remember that water is a resource and it should be measured. And some of the information we have from the UK government is by 2050, we will need an additional 5 billion litres per day of water in the UK. The other thing to consider is there is also a CO2 emission impact of water. 6% of all UK CO2 emissions come from the use of water. So using a chiller is going to cut down how much water is used and also how much CO2 is output. Then, of course, there is a financial cost. Okay, the average price of water in the UK was about £4 per cubic metre. If you consider that if you're using a 3-litre rotary evaporator, that uses roughly 230,000 litres a year, which means you're paying just over £1,000 a year in running costs, just running cold water through a condenser. So if you have a lab full of these, that's a significant financial impact on the running costs of a laboratory. So they are the main reasons why any particular lab or lab manager might be considering using a chiller in their lab. So the first question I have for you quickly is, and this will help drive our conversation forward, if you're looking at a chiller, what are your main reasons for looking at it? Is it the reproducibility? Is it the flood risk? Or is it the sustainability and costs? So if you could spend a moment just to click one of those buttons that's popped up in front of you, that will help us to understand exactly now why you guys out there are potentially looking at chillers. And my colleagues in the background are going to feed through some of the answers to me in the next few minutes. In the meantime, I think I'll push on forward while I wait for those results. Hi, Neil.
Hi, yeah, we're getting some interesting results coming through. 62% are going on a reproducibility and temperature range. We've got 6% going on flood risk and 30% going on sustainability and cost. So obviously temperature control is the key driver factor, then sustainability from there.
My personal impact on that is the flood risk is something no one thinks about unless they've had a flood, and then they'll think about it. But it is indeed interesting that the key driver is reproducibility and temperature range. Yeah,
helps drive better chemical reactions and things like that. So
okay, so let's move forward, understanding that what you guys are thinking about. Okay, so the chiller advantages, obviously, having said that, how does it solve these particular challenges that we've come through? Okay, so reproducibility and temperature range. So obviously the key point here is that you have no seasonal changes. Okay, so if you have a chiller, you're going to have the same temperature water running through your system 24/7, 365 days a year. You also have the ability to go down to about -20 degrees C, which in particular, if you're working with volatile organic solvents, can be a real benefit. Okay, on the flood risk, okay, basically if your pipe comes off your device, then only the contents of your chiller is going to go onto your lab floor. So a typical chiller has 5 or 6 litres of fluid. You're only going to have 5 or 6 litres. If you're running a tap through a hose, obviously you've got a whole weekend of water going through your lab. And then finally, on the sustainability and cost, it's not a black and white answer to that. So I'm going to talk a little bit about sustainability and cost, because not all chillers are the same. You have to remember that chillers also have an environmental footprint, and that is related to the refrigeration gas that's in the chiller and also the power consumption of the chiller. So we'll talk quickly about that. Hopefully, most of you understand how a chiller works, and the chiller works exactly the same as your fridge or your freezer in your kitchen. Okay, so what you have is a volatile gas that is a gas at room temperature. It's compressed, and this is a dynamic I pulled off of the web. It's compressed by the compressor into a liquid, and then it goes through an expansion valve, which you'll see at the very bottom of this diagram. As it goes through the expansion valve, it evaporates, and obviously as it evaporates, it absorbs energy, and that's where you get your cold zone. After the compressor, it's compressed, and that's where the heat is. On your radiator at home, on your fridge at home, that's the black sort of fans at the back of the fins at the back of the fridge, which get warm. And obviously on the chiller in your lab, that's the front of the compressor, the front of your unit, where the heat is expelled into your lab. The key point of a refrigeration gas is it needs to be a gas at room temperature, but be able to become liquid when it's put under pressure and under a very slight pressure. And that's what makes it efficient, in the fact that it will absorb heat by evaporating in the evaporation coil. So the next question is do you understand or do you know the type of refrigeration inside your existing chillers? And this is a second poll so that we can talk quickly about what type of refrigeration gases there are in your compressor. And I will go through these briefly and quickly so that you can understand how important the gas is to the sustainability of your units. That maybe some of the older units will have HCFCs, some of the really old ones will have CFCs. You may even know the R number. Neil, have you got some information coming through?
Yep. We've got some votes coming in through. There's quite a lot. Over 50% of people don't know the refrigerant they're using in their chillers. And then 4% is HCFCs, and 39% I don't even know the R number. So
Okay.
there's quite a lot of people that are not aware of the refrigerant they're using them and what impact that will be having on the environment and what's around them.
Okay. Honestly, guys, that is not a surprise at all. That's fairly typical. So what I'll do is I'll talk you through how to understand the environmental impact of your refrigeration gas and how to find out what gases your chiller currently has. This is information that is coming out through legislation, through lots of marketing and developments from companies, and it's important to try and understand the differences. So the first thing to recognize is the first refrigeration gases were CFCs. Okay, now all refrigeration gas is given an R number. Okay, so the first CFCs were, for example, R12. Okay, and these were developed in the 1960s, and they were actually banned in the 1980s. Okay, as both a refrigeration gas, and they were used in aerosols and many other applications. These were replaced by HCFCs in the 80s and 90s, and these had R numbers like R134A. So the A, the postscript, and they had 3 numbers there, and these will give you an idea of the sort of age and the development of your refrigeration gases. And now the world is moving over to what's known as natural refrigeration gases, and these have numbers like R290, so that the prefix 2 is the important number there. And I will explain what these mean, and what the impacts of them. So CFCs are ozone depleting, and they're also toxic. Okay, which is obviously why they were banned in the 1980s. The HCFCs replaced these in the 80s and 90s, and they are significantly better, an order of magnitude better. Natural refrigerants are even one step even further. And the impact of these gases are measured by understanding what's called the CO2 equivalent, which is gram for gram, how much is a gram of your refrigeration gas equivalent to 1 gram of CO2. Okay, and it's usually measured by tons. So here is a quick graph so that you can understand roughly the equivalence of. So if you consider 1 ton of CO2 is the same, 10,000 tons of a CFC is equivalent to 1 ton of CO2. which is why those gases were very quickly phased out in the 80s and 90s. If you go to the 80s, 90s, 2000s, you have the HCFCs, and that is 1 ton of HCFCs is equivalent to 1,400 tons of CO2. And then if you go to natural refrigerations, which are the modern gases, you can see they're pretty close to 3 to 1, which is pretty close to equivalent to 1 ton of CO2. So you can see why legislation and developing research companies like JULABO are moving more and more towards natural refrigerations to replace these gases, just to decrease the environmental impact. Right, you've already said a lot of you guys don't know how to find what's your gases inside your unit, or you don't know what gases are. So rather than going into the poll here, what I'm quickly going to do is I'm going to show you how to find out. So since about the mid-80s, on the back of every refrigeration device, and this includes your fridge at home, but it also includes your chillers in your lab, on the back of the unit, you will find a silver label like this, which needs to contain the model, the serial number, the CE mark, and now the UKCA mark. But it will also have, if you can see in the blue circle there, the refrigeration and the filling weight. Okay, so you can see in this particular unit, the refrigeration is R290, which is the natural refrigeration, and the filling weight there is 33 grams. And you can see at the bottom, it even gives, since I think about the last couple of years, it gives the CO2 equivalent and the GWP potential, which is the global warming potential. Hi, Neil, I see you popped up.
Yep, so I'll just give you the results. This one's a bit more of a positive. The 62% of the people know where they can find these figures and details. 37% say no, they don't. Okay. So that's the results from that, Bob.
Okay, so that's interesting. But if you look for this serial number plate that should be on the rear of your unit, that will give you the gas and the filling weight. So this particular unit, which is our model 450F, you can see has R290 and it has 33 grams of refrigerant in it. Okay. The second, so we've talked about refrigeration gas. So the key point there is if you're looking for the most environmentally friendly refrigeration unit, then what you need to be looking at is a natural refrigerant, which is an R290 or R2XX number. The second thing to look at is power consumption. Okay, most units run constantly. Okay, so most chiller units that you have, you turn it on, you set it at, let's say, 10 degrees C, and you walk away, and they are designed to run 24/7, exactly the same as your tap water. Okay, there are two things to consider. The first is that it's consuming electricity all the time, and the second thing is obviously wear and tear and any moving parts. JULABO is currently working with two specific developments with our new product range. The two areas of that are frequency control compressors. So instead of running the compressor 24/7, the compressor speeds up, slows down, depending on demand. And the second thing, which sounds really, really simple, is a timer function. So our new chillers is the Vellegro range. Okay, so in there we have state-of-the-art electronics. We use natural refrigerants. We keep the units nice and small, and some of the larger units will have frequency control compressors, which allows them to use less electricity. But because we're using state-of-the-art electricity, it also means we can put something such as a timer on it. So how much energy can you save using these really what are quite simple, quite straightforward steps? The key answers to that we needed to measure. So we actually did an experiment over the last month or so, and we set up, and you can see in this diagram here, you can see it's a Vellegro chiller, and we set it up with a very simple stainless steel Bookie reactor. So we just setting a standard 10 degrees C. Inside the vessel, we put a quarter of a litre of water, and we tried to work with what would be a very, very typical application. So that is, you're going to be working in your lab 8 hours a day. You're not going to be working overnight. You're not going to be working all day. So we just set it up to work 8 hours a day. And we did a back-to-back comparison with some of our existing units that are being replaced by the Vallegro unit. And I'll be honest and say that the results quite surprised us. So we compared it with two specific units with very similar specifications. So we have an FL601 and an F500, and the numbers there mean the cooling capacity. So the FL601 has 600 watts of cooling, the F500 has 500 watts, and these two units are going to be replaced by our Vallegro 500s. So the energy saving in a lab, just by using the timer on the 500 watt unit, was a 20% saving in electricity, and on a 601 was a 60% saving in electricity. And over the lifetime of an instrument, you can imagine that is a significant saving in running cost of the unit, giving you a return on investment or a payback period which is significantly shorter. But now the real key question is, how do you correctly size the unit? If you look at any chiller manufacturer, and JULABO has over 20 different models available, how are you going to decide which unit is right for your application? There are three things that you need to consider. And when Neil and we visit customers, nearly always the customer says, I want water at 10 degrees C at a flow rate of this. Okay, but there are three things you need to consider: the flow rate or the back pressure, the temperature range that you want to work at, but also the cooling capacity. And Neil and I will be the first to tell you, most customers don't actually consider the power requirement. They think they need water at 10 degrees, they need a flow rate of 5 litres a minute, but they're not actually sure of how much heat is being removed by their application. So we'll go through the variables. So the flow rate is an obvious one. Are you going to be running one condenser? Are you running 4 condensers? Are you running a big condenser or a small condenser? Okay, so the first question you have to ask yourself is a flow rate. Using your existing application, obviously that's very, very easy to measure. Get yourself a bucket and a stopwatch and you can measure that quite quickly. The second thing is the temperature range. Most tap water usually runs at a temperature of between 10 and 15 degrees C. Okay, however, if you're running with some organic solvents that are particularly volatile, you may want to run at 4 degrees or even lower. We have customers who are running at -10, -15 degrees. This is an important question that you need to consider the day you're looking at a particular chiller. And finally is cooling capacity. Yeah, how much power? Okay, are you running one very, very small application or one very, very big application or lots of small applications? And again, this is something that a lot of our customers don't consider. Again, what I would suggest you do is either chat to someone who has seen it all before, like your colleagues at JULABO, or alternatively with your bucket and stopwatch again. It's really, really easy. It can be easy to calculate this if you have the flow rate. You can measure the temperature going into your application, so out of the tap, and then out of your application, so going into the bucket that you're measuring. And then you can do some simple mathematics, okay, to calculate the cooling capacity. This is fairly standard 16, 17-year-old mathematics. So the power required is equal to the mass. So that's the flow rate over time. Yep. The heat capacity, if you're simulating water, the heat capacity of water is 4.2. You can look this up. Change in temperature divided by time. Okay. Now, we at JULABO are more than happy to help you with these calculations. We do it on a daily basis to make sure that you get it right. Okay. And the one thing that a lot of our customers always omit to think about is how much heat losses that you're going to lose to the environment. If you're running particularly at low temperatures and you see condensation or ice forming on any of your pipes and stuff, obviously that is absorbing some of the capacity of the chiller, and you need to take this into account with your calculations. Conclusions. Okay, JULABO has now been developing chillers for more than 50 years. Okay, and all of the time we are looking for products that are better performing, more precise, more accurate, but above and beyond that are more sustainable, so having less and less impact on the environment. And we're currently doing that in 2 ways: in carefully selecting the right refrigeration gas to have the minimum impact over the lifetime of the unit, but also using the less energy. I would encourage you to reach out and talk to your JULABO representative, distributor, partner, whoever it is, to ensure that we help you to get the right solution. It's in no one's interest to have an undersized unit. We are here to help you choose the right unit. We will always arrange a demonstration, or we will always come and do the measurements for you to ensure that we make the right calculations and that you have the right solution for you. You can see some of our older units here. We recently ran a competition to try and find the oldest unit, and it was nearly as old as me, I have to be honest to that. Okay. Our new products, as I said, we are offering not just lower CO2 equivalent on the refrigeration gas, but significantly lower energy consumption, which means lower running costs and a faster return on investment. Questions and answers. So Neil, you can pop up again here. Have we got any questions anyone's asking?
No, it's actually been very quiet in the Q&A, but please feel free to put any questions on there that you'd like to put to Gary and myself, and we'll do our best to answer them when we can. So as I say, we have a hand just go up there. No, it's gone away. So
they're just waving, a friendly wave, yeah. Yeah.
Oh, there's a few people they're trying to wave their hand. If you could put your questions into the Q&A section of the webinar, we'll be able to then respond to them from there. Thank you.
Yeah, so one of the key things is obviously one thing we have at JULABO with myself and Neil and our colleagues is we have lots and lots of experience with installations in diverse and challenging applications. The key point is to reach out to us, because we're more than happy to arrange a demonstration. We're more than happy to turn up with a bucket, a thermometer and a stopwatch and help you to determine how much cooling power you need, what temperature you need, what units you need. It's our job to make sure that you get the right units for your application, and we're more than happy to invest the time and effort to do that. Certainly in the UK, we have quite a wide range of units available for demonstration, and it's what we do on a day-to-day basis, is helping guys to make the right decisions for their application.
I've just put a post out, but I think there isn't any questions. I think we're clear.
Okay, and like I say, I encourage all of you, reach out, have a chat. Oh, I've got a question just come in. I have a chemical reactor of 5 litres and I want to cool down from 180 to 100 in 30 minutes. What will be the cooling capacity required? Right, I am. Neil, do you want to do a quick calculation on that? The key question on the chemical reactors, first of all, is 180 to 100. You need to know, obviously, what's inside the reactor. Okay. From 180 to 100, it's not going to be water, it's going to be an organic solvent, which has a slightly different heat capacity. So we make some general assumptions from that. So it's I would assume a CP of 2.1 instead of 4.2 because it's an organic solvent. Dropping 80 degrees in 30 minutes. Neil, are you doing the calculation, or do you want me to?
I'm just doing this right now. So far.
Okay, if you do that calculation, then
Sure.
another participant has said, will it be shared with the presentation be shared with the participants? Yes, of course it will. Yeah, we will share this information with you. If you've registered for that, you'll be able to see that. Okay, I think there is one.
Yeah, I do apologize.
Okay, someone has asked a question about -50. Okay, you have a unit that goes to 250 degrees. Okay, we have an entire range of units that cover the range from about -95 up to over 250 degrees C. So we have a whole range of units of different sizes, different powers and different capacities. So what I would encourage you to do is, if you have a specific application, like the person who asked about the cooling capacity, is you need to give us a bit more details, because on -50 we have half a dozen units at least, and it just depends on which one is right for you, going up to 250. So in the range -50 to 250, we probably have 20-30 units, and they can range from heating or cooling a reactor of 1 litre to several hundred litres. So obviously the size of the unit, obviously the budget depends very much on what you want to do. So yes, we do have a unit that goes -50 to 250. In fact, we have a bunch of them. So why don't you come to us and talk? Neil, did you finish your calculations?
I haven't had a chance to do the calculations, but what I suggest, as this is to do with a reactor and not with chillers, and there's probably a little bit more detail to do than and hold people up, what we'll
Okay.
do is perhaps reach out to Elizabeth and follow up on that as a private matter.
Okay, we'll do that.
Okay, no problem.
Okay, going through some of the other questions. What is the lifetime of a chiller? How long is a piece of string? Okay, the honest answer to that question is it depends entirely on how hard you're hitting the chiller. But typically, on average, the lifetime of a chiller is about 8 to 10 years. Okay, obviously, if you're doing very, very demanding applications, it can be a little bit shorter. If you're doing something not so challenging, it can be a little bit longer. But 8 to 10 years is fairly typical. Okay. Another question, which parts according to factory recommendation have to be replaced per year or at least in the first 5-10 years? How much do they cost? Again, depends on your application and what you're doing. However, I would say to you, as a rule of thumb, the only thing that you need to think about changing every year is the fluid in the chiller. Okay, in the type of application we're discussing, which is replacing tap water, most people will use tap water or they'll use a glycol water mix, and I would recommend chasing that every year. Every 5 to 10 years, depends on how much you're heating, how much you're hitting the unit, how hard you're doing it. One example, um, typical preventative maintenance we have on the unit: change the fluid. You also need to vacuum out the front of the unit, which is where the condenser is, to ensure it's clear of fluff and stuff like that. But that's all the routine maintenance that we recommend on our units. Some customers, depending on the application, will also want calibration of the temperature sensors as well. But what I would say is every year, change the fluid. That's about it on routine maintenance. Okay, I'm going to go through again. Can the chiller be connected to a PC and monitor and record the temperature? Yes, it can, is the answer to that. On the depending on the model of the chiller, there is RS-232, there is also USB, and there is also option on Ethernet connection on some of the units as well. Lifetime of the unit, we've done that. Can we give one example calculation with numbers? I'll tell you what I'll do is I will put an example on the presentation that we send to you, and what I'll do is I will come up with a very typical example. I will put it on the last slide of the presentation before we send it out to you guys. How does that sound? I can't see any more questions. Could you see any more questions, Neil? Have I missed anything?
No, I think you've covered most. I've responded back to some of the more technical questions that came up earlier. No, I think we've covered everything there. So, yep, no, I think we've covered everything. There's one just came in. Perfect.
Okay, let's have a look. That's good. Okay, yeah. Okay. Do we need a software to record? The answer to that question is of course you need you need a software package. However, if you go to our website, there is a free to download software that can do basic logging of data. Okay. However, there is also links that you can upload into there so that you can do different commercially available software which will allow you to talk to your JULABO.
Yeah. There's just a very important question just come in. Is the viscosity of the heat transfer fluid important? Well, to answer that is simply yes, it is very important. I'm sure Gary will probably go into a little bit more detail. Gary, do you want to answer that one?
The main impact of viscosity is flow. Okay, so if your fluid, the more viscous your fluid is, the harder it is to flow around your application. For our units, we recommend a viscosity of less than 50 centistokes, which will allow you to have good flow, which covers almost all applications and fluids. But there are a range of fluids available covering different temperature ranges and different demands. But anything above 50 centistokes, you start to get a challenge with flow. Someone's just asked, do we get a link to this webinar? Yes, we're going to send on a copy of this presentation at the end of it. And like I said, I am going to add a slide on to the calculations, which show you how to calculate how much cooling capacity you need. Okay, so I will put a real world example on so that you can then feed your numbers into it and come up with the calculations.
Right.
I'm liking all these questions. When you mention changing fluid every year, are you referring to the silicon oil, I believe? Okay, changing fluid every year is just routine maintenance. And again, the lifetime of your fluid depends on what you're doing. Okay, some fluids might last 30 years. Some will not last 6 months. And it just depends how hard you're doing it. Silicon oil is used in temperatures outside where you're going to work with water or water glycol. So below minus 15, 20, above 80 degrees C, you'll want to use silicon oil. Silicon oil has a much longer lifetime if you're not going above 200 degrees C. Above 200 degrees C, depending on what chiller you use, silicon oil can have a shorter lifetime. But if you're using silicon oil, it lasts longer than water glycol. When you're running at low temperatures with water glycol, what tends to happen is over time the glycol breaks down, the viscosity increases, and you just need to top it up. It's a case of keeping an eye on your fluid. And I mentioned every year because it should be start of your standard monitoring process.
I'd like to just add to you your points, Gary, here. Obviously, the products we've been discussing today are chillers. Obviously, the higher temperatures, the ones that are going from minus 90 all the way up to 250 degrees C, are process systems, which are high temperature control systems. So they are completely different to the systems we've been discussing in the presentation today. So the chillers that we've been discussing today are generally going to be using either tap water or glycol water mix for their thermal fluid that they're going to be using. So for that, with the lifetime of the water, you're going to be wanting to change, because if it's just tap water, there's possibility of over time contamination getting into your water. So you're going to be wanting to do a regular change of that tap water to stop any contaminant, or add an additive such as our aquastable to the chiller water to stop any growth or any sort of microbiological growth into the water. So with regards to changing that regularly, that's something to keep in mind for the chillers side of it. Obviously, Gary's mentioned about the Prestos and our higher temperature systems, our circulators and our Presto systems.
Okay, so another question popped up. I'm enjoying these questions because, like I said, I like an interactive presentation where we have a discussion. What are your recommendations about how to correctly choose the pipes for the chillers? This is both simple and also very quickly overlooked by a lot of people. So the first thing you need to think about is how far away your chiller is from your application. Okay, so obviously you want to keep that distance as short as possible just for efficiency. What I would say is your first choice is to make sure that your pipes are chemically compatible with your fluid. Okay, if you're using silicon oil, you can't use silicon piping. Okay, so that's the first thing to think. Most people in this type of field, as Neil just mentioned, will be using water or water glycol. So your choices are much wider. I would recommend that you think about the internal diameter of your tubing. Flow is important. And if you have a very narrow internal diameter, you can restrict flow. So we try and recommend a minimum internal diameter of 12 millimeters or half an inch. Okay. The second thing you need to think about is if you're working below about 10 degrees C, you're going to get condensation on the outside of your pipes. So you should consider insulating your pipes if you're working below 10 degrees C. And that's about it really when it comes to pipe recommendation. Try and avoid anything that's going to restrict flow, and think about lagging your pipes. You can get standard pipe insulation. It's available on our website to prevent condensation or icing on the outside of the pipes if you're working below 10. But they are the main considerations I would consider.
Okay. The next question that's come up, Gary, is the degradation of fluid. Is there a good way to see degradation? Now, obviously, I know that there's specific things on silicon oil which we can go into, but obviously with water and glycol water, you're really looking out for contamination within the fluid. But I'll let you go into glycol water while I carry on with the questions.
Yeah, okay. I mean, the big way to see degradation of glycol water is a viscosity change. Okay, the glycol, whether it's ethylene or propylene glycol, will degrade over time, over significant, depending on your application. And what will happen then is your viscosity will start to increase as you go lower in temperature because your water content is higher, and so you get icing. So it's just a visual check more than anything else. There is no specific thing, but you will just notice that it goes. Thanks for your answer. Last question, what makes a fluid good? It works in your temperature range and it has a low viscosity. It's that simple. Yeah, so if you're working at -20 to +100, does it work in that temperature range and is the viscosity good? That's it. Okay. There is someone who's asked, in what temperature range can you use water? Okay, I would recommend temperature water is not below 4 degrees and not above 80 degrees. Below 4 degrees, what you will have is in the evaporator coil and in the cold part of the chiller, you'll get ice build up. Okay, so if you're working below 4, in fact, I would say if you're working below about 10, you would probably want to consider using glycol water. Okay, acceptable conductivity of that water. Most chillers will have some stainless steel parts in that, so I would recommend not using DI water. DI water tends to corrode stainless steel. It's much better to use bog standard tap water. Okay, and if you're working in the temperature range of 10 to 60, 70 degrees, you're going to have no problems with tap water at all. The one thing you have to look out for is any algae growth. What you tend to have, especially if you're working at like 30 degrees, is you can get algae buildup, and strangely enough that looks like a grey powder in your water, so you may want to consider adding some sort of anti-algicide. If you look on our website, we call that aquastabil, that just prevents algae from growing in your water. Lots of questions coming through. Another one coming through: is turbulent flow more efficient than laminar flow? That's a very big open-ended question, and the answer to that question is yes on very large reactors. On anything below about 10 litres, it doesn't really matter. Okay, so if you're considering a very large jacketed reactor, then you will probably want to have turbulent flow. Big open question, that with lots of debate, and the million-dollar answer to that is it depends. Yeah, so I'd say on very large applications that can be important, but to be honest, on smaller applications that doesn't become much of an impact. Okay, I think it's a good time to say we've done the 45 minutes. What I would encourage you to do is to reach out to us at any time if you have any questions. You have all of our contact details. Our job is to help you and to understand how we can or even cannot help you. Like I say, we will be sending a copy of this presentation around. I will put a real world example on that, and I will make sure you have contact details so that you can reach out to us at any time. I'd like to thank you all for coming. Thank you very much for your time. I know how important time is for people. I hope that you found it useful. And thanks from me, Neil.
Yes, thank you very much. It's been a good, interesting. I love the feedback at the end. That was really good, and we've had a good attendance for this. So again, thank you everyone for your time.